I think machine learning is super, super interesting. In fact, when I was graduating from my undergrad with a BS in computer science, I actually felt like I didn't know enough about the topic and opted to do a master's in computer science with a specialization in machine learning. A few years back, I got the opportunity to lead and work on a machine learning project as part of my full-time work as a software engineer at Microsoft. And if you clicked on this video, I would say that in many ways, it can be seen as a failure. Now, what makes an ML project a failure or a success? By all means, I don't consider my ML project that I worked on to be a failure, but if you were to use the metric of having your model and the ETL pipeline and the ML ops deployed to a production environment with a lot of people looking at the results and taking action based on those predictions or classifications, then yeah, I would agree, based on those metrics that my ML project was a failure. I do think I learned so much in the process that I can't see it as a failure. And I think my team and manager learned a lot about just ML in general and our data maturity. So that's part of the reason why I'm going to talk about it today. Now, as a disclaimer, I'm not going to go into too much details, obviously, because this is something I worked on for work. And, someday this project might get revived. So I'm just going to keep it kind of high level and talk about these takeaways that can transfer to all sorts of ML projects and industries. So let's go ahead and get started. If you're new here, first of all, welcome. Second of all, be sure to like and subscribe. But anyways, the point that I was getting at is if you're new here, I work at Microsoft in their high performance computing and AI group. And basically what that means is my team is responsible for maintaining and building out these high performance computing nodes. And what that means is these nodes, when I say nodes, that's basically like computers that make up the cloud in Azure's cloud offering. And customers basically use these specific computers or nodes to run their high performance computing workloads. So they're usually for AI training or inference, because these nodes have GPUs or an accelerator or something that makes them suitable for high performance computing workloads. How this project came about is basically I was interested in machine learning, and my manager is awesome. He knows that, and he kind of was looking out for me and was like, there's this piece of hardware that emits a ton of telemetry, every X minutes, and it comes in all the time, and we don't really use this data a lot yet. We had just set up the data pipeline for it, and the telemetry was getting ingested every X minutes, and there are a lot of failures for this piece of hardware. So an ML project can be trying to predict when this piece of hardware is going to fail using this telemetry before it happens. And that was all fine and dandy, so I went about starting the project, and that's kind of what leads me to the first learning point that is super, super essential. The first point that I really want to drive home is that you should never be jumping into an ML project prematurely. And what I mean by that is, in my case, I was itching to do an ML project. I just finished my master's and wanted to apply a lot of the modeling techniques and things I learned to the real world, and a new data set that was huge, a lot bigger than anything I'd ever worked with, and apply it to my day job. But I think going forward, and people have kind of toyed with other ML ideas and brought them to me, but I'm always very hesitant to act on them now, because I've realized that there's so much that you can do before you get to modeling and making predictions. In fact, it's actually probably like one of the last things that you should do in terms of the data maturity lifecycle or analytics lifecycle or whatever it's called exactly. I don't even remember. But that's the first takeaway that I want to have is you really should be very, very mature, and your team should be very, very mature before you get to modeling and making predictions. What I mean by that is you can really get a lot of business value with just doing data analytics and having rule-based heuristics and things of that nature, because that's really what we're looking for, driving business value and being able to make data-driven decisions. And in lots of cases, you don't actually need to be modeling to do that. You can have great data insights even if you just are smart about, some of the statistics that you pull, and, you might have a great dashboard or something like that. So that's the first takeaway. In our case, the team was very raw. We just set up this new data ingestion pipeline that was streaming, a ton of rows every X minutes, and it was coming in more than we knew what to do with. And in our case, jumping straight to machine learning was not necessarily a good move, because in retrospect, there's actually so much that we could do with just the normal, I shouldn't say normal, but the non-ML aspect of data analytics. The second point that I want to drive home is the importance of having a very clear problem definition. It's not enough just to say, oh, we want to do this blank. You need to say, we want to do this with the qualifications that it needs to do X, Y, Z, for example. I know I'm being super vague, but you'll see what I mean in a second. So for our example here, we want to predict when a piece of hardware is going to fail. That's all fine and dandy, and I went about that process of trying to predict it, and that process was not trivial. I went through the process of analyzing the features. I had set up an ETL pipeline to extract, transform, and load the data as it's ingested, to transform it, to make the features, feed it into a pre-trained model, produces the results, and those results get written to another table, things like that. But that's not enough, because when I produce those predictions, the first thing I get is, okay, is there enough time for these predictions to actually be acted on before the failure happens? And that opened up a whole other can of worms, because I was kind of thinking about the problem in a silo, and I wasn't thinking about the solution and what it would actually take for the solution to be executed. So just because I should say the model that I made produces a prediction that says this piece of hardware X is going to fail in Y minutes, but then there's a team downstream that we never talk to on a regular basis, but team Z, they require 30 minutes notice to be able to actually get to the physical piece of hardware and take it out of rotation or repair it. Things like that is just an example of what I'm talking about. So before jumping into a project, I would really highlight the importance of thinking about what actually needs to happen for your solution to be carried out, if that's your end goal. If your end goal is just to make predictions and then in the long run see how it does, that's fine. But if your end goal is to make predictions on something and have that prediction be acted on by some sort of actor, whether it be human or not, think about what has to go in for that actor to be able to take action on your prediction. So just keep that in mind. And again, it's all about the expectation. And that's a nice segue into the third point that I want to highlight, which is the importance of having a clear goal or performance metric that you're trying to optimize. In many cases, people just default to accuracy without any regard for the true definition of accuracy. In my experience, or in my example, accuracy doesn't mean a lot. We have tons and tons of hardware, and say the hardware produces telemetry every 5 minutes or something, and we're trying to predict failures, and we have one failure out of the 99. So we can just say every single time the model should just predict that there's no failure. And then if that's the performance metric, then I can happily say with a clear conscience that I'm not lying, my model is 99% accurate. Obviously, that's not useful because we're trying to predict failures, but this data set is very imbalanced, so you have to use something like precision or recall. And it's important to have that discussion earlier and explain, the trade-offs of which one you want to optimize, because usually precision and recall, they come at a trade-off, because recall, you're obviously trying to get all of the positive cases and cover as many of those as possible, but then there's an increase of a chance of a false positive. So all that's to say, it's important just to temper expectations or have some sort of clear performance metric that you're trying to achieve, and even better if you could get a realistic number. But in many cases, it's hard to get what a realistic or a good performance metric value is, because if you're doing this for your real job, oftentimes this data is not going to be publicly out there. It's not like a Kaggle data set or something. Honestly, I already think I drove home the main points that I wanted to highlight here. It's just that in many cases in industries, I'm very hesitant to jump to an ML-based solution because there's so much you can do before that with rule-based heuristics and data analytics. And in addition, having an ML project see the light of day requires very, very careful project planning and coordination among stakeholders and understanding of the performance metric. And it also is very dependent on the industry, because having a wrong output from your model can be very, very expensive, whether it is financially or, someone potentially dying or something dying, something like that. I'm just going off the top of my head here. But in cases like that, it can be very, very difficult to have it see the light of day. And it's all dependent on your goals for the project. So in my case, it's a very, very expensive industry, high performance computing. So if I were to say, this particular server is going to go down because of this hardware component, let's take it out of rotation and have a hardware team look at it. That is a very costly decision to make, because these servers are $100,000 plus. So when I say that I don't think my project was a failure, it's because it's a very, very difficult problem space. And I think we learned so much throughout the process. And my team really wasn't actually that data mature at the time. If you're wondering what actually happened with my predictions, it just so happened that my predictions were for these specific pieces of hardware that actually had signs of failure before, and they had actually already failed before the majority of the time when I raised the decision threshold. So all this to say, this just kind of highlighted how we could have improved our data maturity by improving our failure detection steps before jumping to a failure prediction project. Hope this was helpful, and please, if you like this, be sure to hit the like and subscribe button, and I'll see you guys in the next one.